In this video, we're going to begin our look at first-order separable equations. So first-order differential equation of the form dx dt is equal to f of t times g of x is said to be separable or have separable variables. An equation of the form dx dt is equal to f of t over g of x, or dx dt is equal to g of x over f of t, also satisfies what we need for a differential equation to be separable. So what do we mean by separable variables? Now, I know this is going to seem a little weird, and it should, but we have this notation dx dt is equal to f of t times g of x. So this notation dx dt means the derivative of x with respect to t, right? X is a function of t. We take the derivative with respect to t. We can also treat dx and dt as differentials, i.e. some small change in that variable. When we do that, we are allowed to separate the dx and the dt. So we can treat this as dx divided by dt when we think of dx and dt as differentials. If we do that, then we multiply by dt on both sides here, and if we divide by g of x, this equation here can be rewritten as dx over g of x, if we divide it by g of x on both sides, is equal to f of t times dt. So now what we have done is we have separated our variables. On one side of the equation, we only have x's. On the other side, we only have t's. And again, if we had dx dt was equal to f of t over g of x, or dx dt was equal to g of x over f of t, if either of those things occurred, then we would also have an equation where we could separate our variables. I will have a video posted up that will go through why we are allowed to do this whole separation of variables thing, and we can actually treat dx dt as differentials and why we can separate those. So that'll be in a different video. But for right now, we're just going to work with our definition of separable to solve a few questions. So the first thing we want to do is try to determine whether the following differential equations are separable or inseparable. So in this first example here, we see that we have dx dt is equal to, and x squared plus 1 is some function g of x. And here, we can have f of t be the function 1. So if g of x is equal to, so again here, g of x is equal to x squared plus 1, and f of t is equal to 1, we in fact get exactly dx dt is equal to g of x times f of t, in which case this is separable. So our first one is separable. For the second one, we have an x plus cosine of t. There is no way to write that as some function of x times a function of t, or similarly, a function of t divided by a function of x, or a function of x divided by a function of t. There is no such way to do that, so number 2 is inseparable. All right, so let's take a look at the third one here. This third one is x prime, so dx dt is equal to, and then it looks like we have a function with x and t's in it, and it kind of looks like this is inseparable again. But let's notice that if we have x prime is equal to 2t minus 1 times x plus 1, let's go ahead and multiply this out. We get 2tx plus 2t minus x minus 1. So in fact, that right-hand side can be written as a function of t times a function of x. So we again get a separable equation. So this is separable. All right. Let's look at our fourth and final one. As we said earlier, we can split up our dx and our dt. So let's rewrite this as 1 plus t dx is equal to x squared dt. Now, if we divide by x squared on both sides and we divide by 1 plus t on both sides, we get dx over x squared is equal to dt over 1 plus t. And we have separated our variables, right? Everything with the x is on the left and everything with a t is on the right. Notice also, and this is very important, that the dx is in the numerator and the dt is in the numerator. We do not want dx in the denominator or dt in the denominator anywhere. We need those to be in the numerator, but if we have successfully separated our variables with dx and dt both in the numerators, then our function, or our equation, excuse me, is separable. So number 4 is also separable. Here. For the last part of this first video on this section, we're going to just use this to then solve a differential equation. So we're going to take a look at how to do that here with this example 2. So the first thing we want to do is separate our variables. So to do that, we have dx dt is equal to x squared plus 1. We want to separate our variables. That means we want to move the dt up to the right hand side. We do that by multiplying by the differential dt on both sides. So we have dx is equal to x squared plus 1 dt. And of course, we need to move the x squared plus 1 over to the left, so we divide by the function x squared plus 1. And this becomes dx over x squared plus 1 is equal to dt. Now, once we have put it in this form where we have separated our variables, what we want to do is we want to integrate both sides. The left-hand side is integrated with respect to x because we have a dx. The right-hand side is integrated with respect to t because we have a dt. So if we integrate the left-hand side with respect to x, you might just recall that this left-hand side, the integral of dx over x squared plus 1 is arctan of x plus some constant c. For right now, I'm going to call this a C1. The right-hand side is the integral of 1 dt. The integral of 1 dt is just t plus some constant I will call C2. Generally, once we have something of this form, if we have a C1 and a C2, we can just move those all to one side and rewrite it as just a new constant C. So we can rewrite this as arctan of x is equal to t plus some constant c, which is what's written here, right? That is our answer. And so this is our solution to the differential equation. Notice we can no longer put this as x is equal to, or we may not be able to easily write it out as x is equal to some function of t. But that ends our first video. We will continue on with another video. We do several more examples, as well as a third video that will tell us or talk to us about why we are allowed to separate these variables and why that's okay, why we can change dx dt into thinking of it as differentials, and we can separate the dx and the dt. But that ends this first video.